So last time we looked at examples of synchronization. We looked at synchronization of van der Pol oscillators, and we saw that depending on the type of coupling, you could tend towards different behaviors. One behavior was just that the two oscillators, synchronized and ended up on their original limit cycles, but just in phase. Other kind of coupling led to anti-synchronization. In the first case, notice that the coupling terms disappear once they synchronize, which is why they get on the same limit cycle as they used to, right? Other kinds of coupling, they may get on a bigger, on a smaller, or on a distorted limit cycle, right? If once they synchronize, then the coupling terms don't disappear, right? They become something else, some other nonlinearity. We also said that these same phenomena could also be used to describe, for instance, how do you get systems which are nice, stable, but nonlinear, and how would you couple them so that they get some interesting behavior, for instance, anti-synchronization, as in locomotion, for instance. Incidentally, one of these examples was anti-synchronization of two van der Pol oscillators, and I mentioned this was closely related to the original questions of Christian Huygens. By the way, there was for some reason there was an extra H that appears here. That's the correct spelling. So that was closely related to this idea of putting two pendulum clocks on one wall, which communicate from a common signal, right? And getting anti-synchronization. Remember, when we got anti-synchronization, the coupling terms was a common term, okay, common to both oscillators. It was an x1 dot plus x2 dot in both cases. Okay, we also saw that, of course, the same ideas apply to neural oscillators. For instance, this very classical model, the Fitier-Nagumo model, which we could treat in the same way, and which you will also study in the homework. There's other classical models one can look at. So, for instance, something which has been very popular is a model by Tamás Vicek in Hungary, who's been long interested in things like flocking, bird flockings, group behavior in animals, and using these tools, you can analyze these kinds of questions rather straightforwardly, or rather you can analyze the basic versions of these questions in a simple way. So the most basic system you can think of is this system. So you have state vectors, and each of the system is connected to all others in some neighborhood. Okay, so think of flocking, for instance. You have animals, birds, or whatever keep moving around. Okay. And you have connections defined as in some neighborhood, which could be, for instance, defined as a function of distance, but it could be defined as a function of other things. Okay, and so you have basically these couplings, these error terms, which are summed up on all the neighbors of each of the elements. Okay. So again, think of these kind of birds moving around and coupling locally, and so what happens? So you would like to say, well, it's probable that if these neighborhoods are chosen such that they kind of overlap each other, so that basically everybody is connected, right? One system is coupled to others in its neighborhood, and the other system is coupled to others in its neighborhood, and so on, right? So that basically you cover the whole space. So if that's the case, even though these neighborhoods could be time varying and so on, if you always cover the whole space, intuitively it should be the case that indeed they do synchronize, okay? They do tend towards the same state, okay? So how can you prove that? Well, one way is to look at the virtual system. So for instance, this system, so very similar if you want, very similarly to what we did for quorum sensing, but a higher dimensional virtual system. So basically we just take a copy of this system where the neighborhoods n sub I are the same as those of the real system. Okay? So in other words, j is in the neighborhood of I if in the real system xj is in the neighborhood of xi. All right? So you just copy the system yi minus yj. And then you add an extra term, so think again of it as perhaps like a virtual observer, right? Yi minus xi. Okay? So what's this virtual system again? It's a copy of the real system with the slight subtlety that the neighborhoods are based on those of the real system, not the virtual system. Okay. And then you add this extra term. Now, so what can be said about the system? Well, perhaps it's contracting, perhaps not. We'll see that in a second. It certainly has the real system as a particular solution, right? Because the real system, of course, if you start with all the yi being equal to all the xi's, right, then you're going to just follow the equation of the real system, and this term will be identically 0. Right? So from this virtual system, it's clear that the real system is a particular solution of the virtual system. So if we'd like to show this intuitive result, okay, what we'd like to show is that if you take all these neighborhoods and they basically cover the whole space, even though they're changing, so they keep covering the whole space, then everybody will synchronize, okay? So what you'd like to show is that if this is indeed the case, you cover the whole space, this network is always connected, you can go from anywhere to anywhere through links, right? And there's no isolated part. You would like to show that this virtual system is contracting, which will then show that indeed all the systems tend toward the same quantity. Okay, so now this system is contracting. So I didn't mention what K was, right? K is a constant symmetric positive definite matrix. Now, think of it, if we can show that this system is contracting, that any two trajectories of the system will tend toward one trajectory, okay? And so any trajectory of this entire system, again, this the same I equal 1 to n for the virtual system. This entire system will tend toward a unique trajectory. And that trajectory, of course, is the same as the real system because the real system is a particular solution. All right? So remember we said one way to use the virtual system is to show that all the real systems are a particular solution and tend therefore to each other. A more general way is to say that the virtual system has an interesting, by the way, of course, I meant white dot here, right? It's a copy of the system. Another way to do this is to notice that the virtual system has an interesting property. Okay? One solution of the virtual system has an interesting property, and therefore the real system will have this interesting property as well because it will tend towards that solution. All right? So if you look at this virtual system, one solution of it has an interesting property, namely, if all the yi's are equal, right? So if all the y's of the virtual system are the same, then they stay the same, right? Because then this term is 0, okay? And then they're driven by this same term, okay? So if, because this term here is common to these systems, okay? This is not a very clear way to write it, right? The sum is over J. So this term is common to all of these systems. So not only the real system is a particular solution, but then you have this virtual system, and this virtual system has one trajectory which has the following property: if the yi's are equal, they stay that way, right? Because if they are equal, then this term is 0, and then they're just driven by the same term. So, so if they start equal, they stay equal. So, how do we show it's contracting? Well, we look at the Jacobian, okay? So we take an arbitrary vector v, and we look at the Jacobian of this big system, all right? So if you do this, it's easy to show that if you take this Jacobian and then take the quadratic form associated with this Jacobian, you'll have k over all the active links. Okay, in other words, over all the links which belong to these individual neighborhoods of vi minus vj sub k, by which I simply mean the norm of a vector sub k. The square norm of a vector sub k is simply v transpose kv, right? It's the k norm. So if you do this computation, you compute the Jacobian of this system, right, which is really n systems, so the big Jacobian here, and you take the quadratic form, v transpose jv, what you'll find is you have the sum of all these active links, right, all these neighborhoods, of vi minus vj square. And then you'll have the Jacobian corresponding to this term, okay, and this will be simply the sum over the vi's for vj's, j equal 1 to n square, k norm. K norm still being this. Okay. All right, so now this term, so everybody sees where we are, right? We've picked this virtual system. We've noticed that if the yi's of the virtual system start equal, they stay equal. And of course, the virtual system as the real system is a particular solution. So if we can manage to show that the virtual system is contracting, we'll have shown that all the solutions of the real system tend towards the same state. Okay. So that's the only thing we have to show here. So what basically we're trying to show, because we're picking just the identity metric, is we're trying to show that this matrix is negative definite. Okay. To show that it's negative definite, we compute this quadratic form. And we know this is the sum of two negative terms. So that's fine, but maybe not strictly negative. Okay? So we have to see what happens when. So v transpose jv is always negative, okay? v transpose jv is 0 if both terms are 0. Okay? Right? it's clear it's negative semi-definite, but to show it's contracting, we need to show it's negative definite. Okay, so we have to see what happens when we have 0. Okay? Everybody understands that, right? Now, suppose indeed that we have this covering of the space, right? So there's no xi floating around not connected to anybody. All right? So basically the network is connected. All these active links cover everything. Okay? Then the fact that this is 0 is the sum of squares, right? Means that each of these terms is 0, and since we assume that indeed the network is connected, it means for any I, for any j, Vi equals Vj, right? So that's the first thing, right? We have a sum of square terms, right? So that sum of square zeros, each of them is 0. Okay, so if we assume indeed that the network is connected, it means that for any I and any j, Vi is equal to Vj. But if this is the case, of course, this is the sum of all j. So this means, and therefore, has to be equal to 0. Because if they're all equal and they sum up to 0, then they all 0. Right? This term says, for this to be 0, it's clearly negative semi-definite. Is it negative definite? Well, for this to be 0, we would have to have all the Vi's equal. But we also would need to have this term equal to 0. But if all the Vi's are equal, this is simply n times V, right? And so it means they're not only equal, but they're equal to 0. Okay. So if you want, we did step by step, but you see that basically with one line, it's more or less a one-line proof, two-line proof computation of the Jacobian, right? By picking this virtual system, you can show that indeed this is what will happen, namely, although these connections are time varying and so on, as long as you keep a covering which is connected, then everybody will synchronize, okay? And of course, you can have variations of that. You can have variations of that which are very similar to persistence sphere excitation. So you can show that if the covering doesn't really have to be connected, but it has to be connected on time-varying windows, okay? On moving time windows. Okay, questions about that? Okay, so I'm mentioning this because it's a very classical example, but you know there are much more complicated ways to solve it, let's say. Okay. So a few remarks, if you want, on some properties of synchronization. We could make a lot. We'll just limit it to just a few. So let's just assume we have identical systems. And using these kind of techniques, you can give conditions to show when they synchronize, and we'll come back to that a little later. And so the first slightly non-intuitive property that you get from this, of course, is that out of local connections, you can get global synchronization, right? Everybody could just talk to neighbors and so on, but you actually get global synchronization, okay? So global sync from local connections, okay? So that's the basic story, right? And we'll give general conditions for that a little later on. But again, you take these millions of nonlinear systems and you connect them under certain conditions, you'll get this global synchronization, and these conditions typically can be local conditions, okay? Local connections conditions. Okay, now suppose that we do something else, okay? So we take, let's say, 1 million oscillators and we connect them through local connections so that they synchronize, okay? And suppose we drop in there 1,000,001 oscillator and another oscillator, which also connects locally to its neighbors. but its connections are only feed-forward connection. In other words, it doesn't get information from its neighbors. It just connects to it. Okay? The others, you have connections which guarantee the synchronization of the whole system. Here you drop a guy that gives its information to its neighbors, but doesn't get any information from them. All right. So what will happen? So you have this big soup, right, of oscillators, millions of them, or cells or whatever, right? And you drop the system. Connects just like the others, but doesn't get any sensory input. What will happen? Well, you can show that dropping this guy out there still preserves synchronization. Okay, so now this million plus one systems will be synchronized. Okay, so that's easy to show. However, of course, this guy is not influenced by the others. So they will be synchronized means that they will be synchronized to him. Right? So it means to it, right? So it means that you can have a million systems, happily synchronizing, starting at random places far away from the limit cycle and converging to a common limit cycle, okay, or in higher dimensional version of that. You drop in there a system which connects locally one way to its neighbors in this big soup, and now everybody is going to get in phase with it. Right? So whatever the moral implications of that, that's called a leader, okay, is the thing that doesn't look at the, okay, it just doesn't get, everybody is going to synchronize to it, okay, because everybody synchronizes and it couldn't care less about what the others do. Right? So you see also it says with a very sparse change in the system, you can completely change its behavior, right? If these are oscillators, the phase is going to completely change, right? And these are higher dimensional systems, you can have even more complicated things. And if you have, local equilibria, right, systems of local equilibria, it means adding this guy means they're all going to vote for the same equilibrium. Right? Because we said, synchronization when you have multiple equilibrium means you get the same equilibrium, right? So you can have a system with lots of local equilibria, lots of pinball-like system, right? You add this system, everybody get into the same valley, right? Okay? So we haven't shown this here, but I'm just stating it's easy to show, okay? So you can have a sparse change in the system in the form of one extra system connected slightly differently from the others, which can drive the entire behavior. Okay. Now the same story and actually pretty much the same mathematics. Again, this is simple, but we would need 15 minutes for each of these statements. Yes.
Wondering if you did the same, but instead of dropping 1 liter, you dropped 2 liters in the system. Is there anything you could say about how things would?
Yes, it's a very good question, right? So obviously they can't all synchronize because they're all leaders, right? What you're going to get is group primitives. Okay, and actually, for instance, for robot flocking, you could use these things. So in other words, you're going to have splits between things. Okay. If you do things right, otherwise you're going to have a mess. Okay, but basically you're going to have group primitives. Any question on this? So the same math show the following thing. Okay, suppose you have all these oscillators oscillating, right, in synchrony. Okay, again starting from any initial conditions, converging to the limit cycles, and the limit cycle become common and you get the same behavior. And you say, wait a minute, who asks for oscillations? I don't like oscillations because actually my system is a power system, is the power grid, you know, and these oscillations are going to make it crash, okay? Or these oscillations, or I'm looking at the brain of a patient and these oscillations are called epilepsy, okay? And I don't want them, okay? So suppose that oscillations are not what you want and you're trying to suppress them, okay? You're trying to get a system from an oscillatory behavior to kind of a flat behavior, okay? What can you do? Well, you can actually take these millions, let's say, of oscillators, and instead of adding a leader, which gets them to be in the same phase with it, you take two of these oscillators and you add an inhibitory link, in other words, a connection between these systems, a two-way connection, that is exactly the same as you would have if you were trying to synchronize them, or to better synchronize them, but with a minus sign. Okay? So instead of trying to, you have this inhibitory connection. Okay? So in a little as in the Huygens thing, we had these things for anti-synchrony. Okay? But you just do that for two of these systems, one bilateral connection out of these millions of systems. And the result is everybody stops oscillating. Okay? So if you think of it, you know, not being a doctor, of course, but one of the old and rather savage treatment for things like epilepsy was about cutting parts of the brain, okay? Or cutting pieces of the brain to avoid instabilities. Right. This says, in principle, that that's really not necessary at all. Actually, you can add something. Okay? You can add something which is this inhibitory connection, which in normal setting, here we're talking about the fact where oscillations are bad. You know, they're not the normal behavior of the system, right? So in normal setting, these are just this one extra connection out of millions, you know, but they guarantee that you can never have this global synchronization setting in. Okay? So again, very sparse change in the topology of the system, right? Adding one inhibitory connection completely changes the behavior of the system from one system where everybody oscillates to one system where, you know, nothing happens, right? And incidentally, the proof of that, which is similar to the leader proof but just a little different, involves just showing that when we had the system without the inhibitory connection, then of course you could show a virtual system, you could exhibit a virtual system which was contracting and show that everybody synchronized. And you can show that adding this one inhibitory connection makes the real system contracting, right? And so then you don't need a virtual system. It makes the real system contracting. And now it's a contracting autonomous system, a big one, but still a contracting autonomous system. And therefore, it tends towards an equilibrium point, right? So that's, in a sense, the same idea that you have this virtual system, which is not far from the real system, is just a modification, right? But which allows you to show that things synchronize. It also allows you to show that you take a system where things synchronize and you add a little connection, and now it's the real system which is contracting. Okay. And because the real system is large but autonomous, it tends towards the equilibrium point that you can't have oscillations. Okay. And then, of course, you have all the tools because you have all the contraction rates and so on. Remember, the synchronization rate is the contraction rate of the virtual system and so on, right? So and of course, you can compute the contraction rate of the systems once you have inhibition. Because you have all the tools, you can also say, well, you know, suppose I want to suppress these oscillations as fast as possible, where should I pick my two systems? Right? You have all the tools to be able to do that. Okay. All right. So now there's a lot of talk on the various names in networks of the notion that some behaviors are robust and some behaviors are fragile. You can, in a sense, this says that you have very sparse changes in topology can create big behavioral change in the system. So in the sense, the system is fragile to topological changes. But you can also show, because you have these virtual contracting systems, the system is very robust to parameter changes. Right? Remember, if you have a contracting system with a bounded disturbance, then you, instead of tending towards a trajectory, unique trajectory, you tend toward the ball, right? But the size of the ball is just proportional to the disturbance. Okay? So you can show that the synchronization is very robust in the sense that parameter changes give small changes in parameters, give small changes in small synchronization errors. Okay, but at the same time, it's very fragile to changes in topology. Okay. It also says, for a robotic system, it's very easy for an extra robot to sneak in and make the behavior of the others be very different. All right. Questions about that? Okay, so these are just a few, and there's more, but kind of few slightly non-intuitive properties about synchronization. Okay, questions about that? Okay, so let's talk a little, let's talk a little about more general tools, if you want, for synchronization, in particular, or more general result, if you want, for synchronization, and in particular, what can be said when you have different systems. Okay, so if you have, we did things for the moment in synchronization for identical systems, and we said, well, it's robust, so if you have small variations. But what about, frankly, different systems? Okay, and these ideas also are, in the sense of what are interesting invariant systems, are closely related to work by Golubitsky and Stewart on what's called input equivalence. So the idea is, suppose that we have one system. So I'll use colors to define dynamics. Okay, so suppose we have one system, and this system is connected, let's say, to 3 identical systems. Those colors and to some extent shape, okay, to define dynamics. Okay, so this system is connected to 3 identical systems. And the dimensions of the red systems and the dimension and the common dimension of the yellow systems could be completely different. And suppose, for instance, this system alone would be just a leader-follower system, where this one just follows that one, as in the our first example of observers, general observers. So you see that if this one was a leader-follower system, well, this one is also a leader-follower system, and so is this one, right? So these are all going to synchronize, okay? And of course, it doesn't have to be, this doesn't have to be the same dynamics. In other words, it just has to be that there exists a virtual contracting system with this system as an input, okay? And out of which all the yellow systems are particular solutions, right? So if you have a setup like this, where there exists a virtual system which has all the yellow systems as a particular solution, okay, then of course the yellow systems are going to be contracting. Now, you can see that, so you might say, well, it kind of makes sense because you have a symmetric setup. Okay? But it's not really symmetry, as I mentioned before. It's what's called input equivalence, because suppose that you take this system, for instance, and you give feedback to the center. Okay, this is just conceptual, right? It's just to get the idea. Suppose you take this system, it gives feedback to this red system. Again, the dimension of the red system and the yellow system could be completely different. Okay? But the others don't. Okay? So now you don't have a symmetry. Right? It is still true that the yellow systems will synchronize. Why? Because as far as the virtual system is concerned, this is just an input. The red thing is just an input. It doesn't matter what created it. Right? So before it was by itself, now it's influenced by one of the systems. As far as the virtual system is concerned, it's still an input. Okay? So in this setup, the yellow systems will still synchronize, although they're not symmetrically connected to the red system. Okay? Now, suppose now we take these yellow systems and connect them to yet different green systems. Yet different dynamics. Well, you see now that these yellow systems, the little diamonds, right? The yellow systems, we know that they're going to synchronize, and now they're connected outwards to these green systems, so the green systems don't influence them, right? So they're going to synchronize, and exponentially. And of course, once they synchronize, they can serve as a common input to the green things. Right? The same way that this red thing served as a common input to the yellow systems. Once the yellow systems exponentially synchronize, they serve as a common input to the green things. Right? So we'll do some math, right? It's just to get you the idea too. So, and therefore, the green things will synchronize between themselves, right? So now we have three different dynamics, perhaps completely different dimensions. Now we know that this one and this one will synchronize. In other words, we have two far away things, because if there's nothing special about 2 steps, we could have 10 steps like this, right? You have two far away things in the system which synchronize without any direct connections. And they synchronize through completely different dynamics. Right? When you have identical systems which synchronize globally from local connections, of course it's true that the far away systems don't have direct connections, but at least the intervening dynamics are all the same. Okay? Well, the intervening dynamics don't have to be all the same. You can have faraway systems that synchronize going through completely different dynamics. Okay? And of course, you can take this further. So, for instance, you could say, well, I could have this thing compute something else and then feed it back to the center. It would still be true that all the green things synchronize and all the yellow things synchronize. Right? And perhaps feed this one directly back to the center and so on. It would still be true. Okay? So this is, as I mentioned, this notion called input equivalence combined with these stability analysis tools. Okay? Now, suppose we take a system, let's say, composed of 3 subvectors, x1, x2, x3, and x4. So those would be four subvectors, x1, x2, x3, and x4, which could correspond to different colors in diagrams like this, okay? And suppose that one has an invariant set corresponding to some particular synchronization pattern. So for instance, we could say it could be x1 is equal to x2, and then perhaps x3 is equal to x4. Okay, so we have an invariant set, meaning that if you start x1 and x2 being the same, and x3 and x4 being the same, then they'll stay that way. Okay. Now, so this gives us a big vector x, right? So this condition here can be written as a matrix times x equals 0, this particular synchronization condition. And what is this matrix? Well, for instance, it could be identity minus identity of the dimension 1, right? 0, 0. And then 0, 0, identity of dimension 4 minus identity of dimension 4, 0. Okay, these two conditions are equivalent to writing things this way. Okay. So this thing we could call matrix V, right? It's a constant matrix, not square in general, which corresponds to a particular invariant set of the system. In other words, a particular synchronization pattern such that once we start there, we stay there. So one can show the following thing. So consider a system x dot equal f of xt and an invariant set Vx equals 0. More generally, it could also be Vx equal constant. So you have a synchronization pattern which you know exists. The question is that, is it the only one? And also, starting from anywhere, do you tend towards that? Right? So for instance, it could be a particular gate in a robot, right? Robot which tries to mimic an insect or a lion or a humanoid, right? So it could be a particular gate which corresponds to a particular synchronization pattern. And the question is, suppose the system is not in that gate, does it tend toward it? Okay, or is it going to do something completely different? Okay, so the question is, you have a system, of course not necessarily contracting, just a smooth nonlinear system. You have an invariant set for the system. Is it the case that all trajectories of the system tend towards an invariant set, meaning nothing else happens? Okay? Well, so you can give a sufficient conditions which can be made a little more general, okay, but we'll stick with that one, okay. So all trajectories converge exponentially to the invariant set defined by Vx equals 0 if the reduced order system, typically reduced order because you have these constraints, y dot equal v f v transpose y is contracting. This theorem is for a constant metric. You have a slightly more general condition for a general metric. So what does it say? It says you have your original system, you have an invariant set of this system. You can show that starting anywhere, you tend towards this invariant set. So for instance, there, if you apply it to this system, it would mean that starting anywhere, you tend towards all the yellow synchronized and all the green synchronized. Right? So you can show whether it's the case that it tends towards this invariant set by looking at this system, right? So remember, V is kind of a rectangular matrix, so it's a lower order system. V, F, V transpose Y, all right? And if this system is contracting, then the original system indeed tends towards Vx equals 0, and so nothing else happened. You know, starting anywhere, you tend towards a synchronization pattern, for instance, x1 equal to x2, x3 equal to x4. Okay? And of course, there's nothing special about this synchronization pattern. For instance, you could have minus x4, right, in which case you would do this, right? It's just any linear combination, right? See, you could say, well, you know, these two are synchronized, these two are anti-synchronized, for instance. It's fine as well, right? It's just any, this theorem applies to any constant V. Okay, or you could say x4 is equal to x1 plus x2 minus x3 would be a third constraint, right? Any linear constraint. Okay. So it's easy to show this, right? Actually, the way to show this is that to show that this is a good virtual system, right? Which is very easy. It's a few lines, right? And so you can get this result. Okay. So now notice the Jacobian of the Y system. Since V is a constant matrix, it's simply of the form df over dx, right, computed at V transpose Y, right? V transpose. So in other words, the Jacobian of this virtual reduced order system is like a projection of the Jacobian of the original system onto a smaller space. Okay. And intuitively, and we can make that more precise, but what is this smaller space, right? It's basically what happens in transversally, right, to this invariant set, right? So you have this invariant set Vx equals 0, that's a plane, right? And you want to show that it converges to this invariant set, right? So the Jacobian for this is that. It's the projection of the Jacobian in the direction towards the invariant set. So based on that, you can show that you can show a number of things, because once you have this, then you're back in algebra, right? You can use all sorts of results on matrices and projections of matrices and things like that. Okay. So for instance, suppose that you have one invariant set, let's say MA, defined by V sub A times X equals 0, and another invariant set MB defined by VB times X equals 0. And suppose that MA is included in MB, then the lambda sub A, okay, so lambda sub A is the contraction rate of the virtual system Y sub A, right, corresponding to V sub A, is going to be less than the contraction rate of the virtual system corresponding to V sub B. Okay. So this is just an algebraic result, okay? So in other words, what does it say? It says that if you have an invariant set which is more precise than another one, it's included another one, then you're going to converge to it slower than the bigger one, which makes sense, right? So for instance, you have one invariant set which has x1 equal x2, and a more precise invariant set which is x1 equal x2 equal x3 equal x4, right? Then the contraction rate towards the bigger one, sorry, the contraction rate towards the more precise one is going to be slower. And this is actually something that one can use in applications a little similar to what you do in the homework, where, for instance, you have an image and you modeling each pixel by a neural oscillator driven by the intensity of the, well, let's say you take the image, it has pixels, and you put another layer which is driven by the pixels, and where you have a neural oscillator everywhere. Okay? And the idea is you'd like to basically things to group and create synchronies corresponding, for instance, to blobs in the image. Okay? But you don't know where the blobs are. Okay? So that's the solution. So in other words, the synchronization pattern is the solution. You don't know it in advance. Okay? Do you understand the setup, right? You have pixels that drive neural oscillators, and you want to connect things so that the system, gets a synchronized region corresponding to pixels of the same intensity. You don't know that at the beginning, right? You don't know what's supposed to synchronize to what, because that's precisely what you're trying to look for. So you cannot apply this directly to the real invariant set because you don't know it, okay? But this algebraic remark is true even if things are not invariant sets. This is just due to this property of the Jacobian, okay, projections of Jacobian, okay? So what are you going to do in this image? You're going to make sure that if all the pixels happen to be equal, then everybody would synchronize, all right? And that will automatically guarantee that, if they are equals in regions, then they'll synchronize by region, because it's a less precise thing, right? Saying that this region synchronized, that region synchronized is less strong than saying that this region is synchronized happens to be synchronized to exactly the same thing as this region, right? So it says by forcing a condition on a set which you're sure is a particular case of what you're looking for, then you will let the system do the computation and figure out what's the invariant set. Okay? But you will converge to that invariant set. And you have an example very similar to that in the homework. Okay. So we're going quickly through those just to give you some general idea. But you see, you have a reasonably systematic way of determining, possibly complex global exponential convergence of two possibly complex synchronization patterns. And of course, you can apply that, let's say, in closed loop. You can say, what control law should I use to get from this synchronization pattern to that synchronization pattern, right? Okay, and that's, of course, the control law, which in closed loop, which will make this condition verified for the synchronization pattern you're looking for. Okay. So now we can just do a few more technical remarks, if you want. Okay. One is that we've done this in continuous time, but you can, of course, do it in discrete time. In which case you have xi plus 1 is equal to f, which may depend on I, of xi and t. And t in that case is more generally noted as I, right? It's the time instant, as it's time. Okay. And so now remember we looked at differential dynamics at fixed time, right? So we can perfectly look at the differential dynamics of the discrete time system because anyway it's at fixed time. So we can define delta of xi plus 1, right? And of course delta of xi plus 1 will be equal to exactly to df over dx times delta of xi. So, right, because remember this is just a differential relation, an exact differential relation applied at some given time instant I. Okay. So before we were looking at the time derivative of the length element delta x transpose delta x, okay? So here, of course, in discrete time, we're not going to look at the time derivative. We're just going to look at the change, okay? So we can look at delta xi plus 1 square. And of course, it's equal to delta x I transpose times df over dxi. I should put an xi here. Transpose df over dxi times delta xi. Right. Okay. And so what do we want? Well, we will say that we want to say under which conditions this distance shrinks, right? And this distance shrinks if the eigenvalues of a symmetric matrix are less than 1, right? As in, the Z transform, right? Except it's so this will be contracting. Of course, here we don't have a metric yet, so in an identity metric, if df over dxi transpose df over dxi minus I is uniformly negative definite. So that this quantity shrinks. In which case, of course, we'll have less than minus alpha sub I delta xi transpose. Now, of course, you can do this with a metric. So you can have delta z transpose equal theta of zi I delta xi. And if you do this, of course, then you look, instead of the equivalent of d over dt of x squared, which was this, you look at the equivalent of d over dt of delta z squared, which is this. And what you get, of course, is a generalized Jacobian. So this is the generalized Jacobian. Notice the theta I plus 1 here. It means theta computed at the next time instance using the algebraic equation of the dynamics. Okay? So you have this generalized Jacobian, okay? And of course, it's contracting if these, you can bound this by another alpha I times delta zi. Okay, so you can do it with or without a metric. So more generally with a metric. And if you apply this to autonomous systems, so f doesn't change with I, and an identity metric, then you get to a very, very classical result in analysis called the contraction mapping theorem. Okay? Right? If the contraction mapping theorem is a particular case of this, with theta equal identity and autonomous systems. Okay? All right. So we have this for the discrete time case, okay? Now let's consider the hybrid case. Not the general hybrid case, but the hybrid case in the sense of, for instance, what you would do in the linear context of a discrete Kalman filter for a continuous system, where you have an underlying continuous dynamics, and then you have discrete measurements. All right? So if you try to build an observer for a system like this, what you will probably do is between measurement just simulate the dynamics, which may or not be stable, and then do updates of your estimate at the time of the measurement. Okay, everybody sees what I say. Let's say in the linear context, a discrete time Kalman filter for a continuous system will have two phases, right? One will be a phase of simulation in between measurements, where you'll simulate the continuous time system. So that will be a continuous update of the state. But of course, if the real system is unstable, then the simulation will diverge more and more from the real thing in between these measurements. And then at measurement, you update the state, and of course, hopefully, the combination of the two works. So of course, you can do this similarly here, okay? So suppose that you have a sequence of a continuous system followed by a discrete system, perhaps followed again by a continuous system, followed by a discrete system, okay? So just a sequence like this, okay? So during the continuous time, delta z increases or decreases depending on what you can bound this with, right? If alpha is positive, it increases. It decreases, but if alpha is negative, it could increase. So if you have, let's say, let's think of continuous followed by discrete, right? So it's a particular case of hybrid systems, right? So during the continuous time, you have something like e to the minus lambda delta t, which is the change. So let's say we have delta z will shrinks by this quantity, okay, at least. Okay, or is multiplied by this quantity, okay. Right? So if you have a contracting system, if you have a continuous system, let's say it's contracting, between two time instants, the bound on delta z will be whatever it was initially times e to the minus lambda t, right? Where delta t is how long this continuous time lasted, right? If the system is contracting, lambda is positive. If the system is not contracting, lambda won't be positive. It means actually the trajectories will diverge during this continuous time. Okay? So okay. Now, so that's for the continuous part. Now, you're taking the system and you do a discrete instance. So it's still the same state, but the update is different. Instead of being a continuous time update, you have a discrete update. That, again, may or not be contracting. Okay? How does it change delta z? Well, it shrinks it or increases it by a certain quantity. Okay? So we have that delta z here is scaled by quantity alpha I. So if we take the product of these two quantities, right? So if alpha I is less than 1, you have a contracting discrete part, and if lambda is positive, you have a contracting continuous part. So, of course, if both the continuous part and discrete are contracting, then this will be less than 1, and the result will be contracting. But you see that they don't both have to be contracting for this to be true. Okay? So in other words, you want this quantity, this condition, to be verified for overall contraction, that the product of the continuous scaling, right, times the discrete scaling at the end of the day is less than 1, so that you have indeed shrunk things. Okay, so maybe the continuous increased, but the discrete decreased more. Okay, or the other way around. Okay, so you see that if you have a sequence of continuous followed by discrete, what you really want is that the product of the contraction or expansion term of the continuous time times the product times the contraction or expansion term of the discrete time, overall is a contraction. Okay, overall gives you less than 1. Okay, so for the continuous time, this would be contracting if lambda was positive. For the discrete time, this would be contracting if alpha I was positive. And what you really want is this. But you see, for instance, you can use this in a number of ways. Okay, so for instance, if we take this Kalman-like context, presumably you know what you're doing when you're incorporating the measurements. You're getting an alpha I which is larger than 1. Okay? But of course, you have no control about the real system. The real system could be expanding or contracting. Okay? So the real system has its lambda, which may or not be positive, okay? Which may be of any sign. All right? So suppose that let's say alpha I is less than 1/2, and lambda is whatever it is. It tells you what should be the sampling rate of the measurements for this to work. Right? Is that clear? Right? Suppose you have a diverging system, right? So minus lambda is positive. Right? So you have a diverging system, and of course you multiply this by the time between measurements, delta t. Right? So this system is going to increase exponentially with the time between measurements. You multiply it by something which is less than 1. So you can immediately solve for, knowing lambda and alpha I, what's my maximum delta t, my maximum time between measurements, to make sure that the combination of these two steps is contracting. And of course, you could do that in a longer thing. Maybe you could take 6 steps rather than 2 steps, and the overall products of all these terms has to be less than 1. Right? You want in a finite number of steps that it works, right? So everybody understands this, right? So you can have very simple sufficient conditions to mix up continuous effect and discrete effects, which tell you, for instance, how often should you sample an unstable nonlinear system if you're trying to build a convergent observer for it using discrete measurements. Okay. So you see it's reasonably easy to play with. And again, it's a sufficient condition. And yes, what I should mention, of course, is that condition is derived by looking at the change in delta z in both systems. So we define the same delta z. So we assume that the metric is the same, right? Now all these thetas are time varying and state dependent. So it says at the discrete time instant, the metric you're using for the discrete system is exactly the metric you're at coming from the continuous system. Right? It's saying the same metric. Right? We're talking about the same delta z, right? So the same metric, because delta z is defined by theta. So we're just saying in this continuous and discrete system, the metric has to be the same. What does it mean? Since everything is state dependent and time varying, it means that the time instance where you change from continuous to discrete, the metric is the same, it's continuous. Okay. So we can see a little example of that, or at least start seeing a little application of this. So let's look at this example. It's called the strap-down navigation problem. Which is something you have in aircraft and also in robotics. Okay. So you have a vector x which defines orientation of a system. You have a rigid body and you have a vector x which defines orientation of a rigid body. And as you know, there's many ways to define orientation, Euler angles and other things, which we'll come back to. And R, it's its position in an inertial frame. And you measure continuously the body angular rate, omega, and the inertial acceleration, gamma, and you measure at discrete times X and R. Okay. And the question is, build an observer for X, R, R dot. Okay. So you have a rigid body, so that could be an aircraft, that could be a robot, all sorts of things. You have continuous measurements of angular rates and acceleration. You have discrete measurements of position and orientation, discrete time measurement of position and orientation. And you're asked to build an observer. We'll give the equations too, right? You're asked to build an observer for this system which generate estimate all the time for position, for orientation, position, and velocity. Okay. Now, incidentally, it's also something. The rigid body, or the body, could be the head, right? Because you have a very similar question when in the head you have in the inner ear you have basically measurements, continuous measurements of angular rate and inertial acceleration and acceleration. Okay. And then you have vision. So this vision is not continuous discrete, but vision is much slower, okay, and also is based on saccades, right? So you get much slower and typically intermittent measurements of where you are. Okay, and you're trying to combine both, right? And so, if, for instance, if you're drunk, it doesn't work very well because this system becomes much slower, and you're much less good at that. So typical question, if you want. And so the equations for this system, we'll state them as with Euler angles, but actually we'll use quaternions, which are more convenient, but I'll explain that next time. Okay. So with Euler angles, you have x dot is equal to h of x times omega, using here Euler angles to represent position. And H is a known nonlinear matrix made basically of sines and cosines of these Euler angles. You have V dot, where V is R dot. Okay. So you have V dot is equal to A, which is just a coordinate change of x time gamma. So in other words, gamma is the inertial acceleration, but measured in the frame linked to the rigid body, and you do a coordinate change, okay, to have the inertial velocity, and then of course r dot equal v. Right. So you have this system, third order in a sense, except each of these are vectors, okay? So really this is third order, and this is third order, and this is third order, okay? So ninth order, but the structure is three systems. And you see also that it has this kind of hierarchical quality, right? Which is just in the physics of the system. So in other words, you have this, which is just a kinematic relation, which relates angular rate and the derivative of these Euler angles. Okay. Once you have these Euler angles, you can compute this state transformation, okay, this coordinate change. Okay. A is a coordinate change, having to do with the rotation of where is this, what is this orientation. And then once you have V, of course, you have another integrator. So in a sense, it's like a series of three integrators, okay, but in a nonlinear version of a series of three integrators, right? And so what we'll see next time is, how would we indeed do this? We'll see it's very easy, right? How would we indeed build an observer for this system, okay, which gives us all the time estimates of x, r, and velocity r dot. Okay, and we'll see it's very easy, and that's a direct application of this formula. So we'll see that next time.